In this video, we're going to discuss issues associated with model specification. Specifically, we're going to talk about what happens when you make mistakes in the models that you choose. Economists have estimated many different models out there, and one of the main sources of dispute among economists is that they get very different results when they choose different model specifications. And in a broad sense, there's two types of specification error. One is you might include the wrong mix of variables in your model, and the other is you might choose an incorrect functional form that captures the relationships among your variables. In terms of the choice of variables in your model, there's two types of errors. One is you might include variables that don't belong in the equation. The other is you might exclude variables that do belong. If you include variables that are not relevant under the conditions of the classical regression model, you still end up with parameter estimates that are going to be unbiased and consistent for all the intercept and slope parameters, and also your estimates of the standard errors are perfectly appropriate for hypothesis testing. And the reason for this is that you can think of variables that don't belong as just variables that have a true value in the population of 0. And on average, you should end up with estimates that should equal 0 since your estimators are unbiased. However, when you include variables that truly don't matter, there's a loss of efficiency because you end up with fewer degrees of freedom and less precise estimates. This generally means that including irrelevant variables will result in higher standard errors and lower t-ratios for the estimated intercept and slope parameters that you've included compared to what they would be if you did not include those irrelevant variables in your model. If you exclude variables that are relevant, the costs are somewhat more severe. In particular, all of your parameter estimates will be biased and inconsistent for all model parameters and standard errors in general, although there is an exception. This bias is larger when the excluded variable is highly correlated with one or more of the variables that you do include, and in that case, the included variable will be picking up the effect of the variable that you omitted. It's also going to be larger if the omitted variable has a relatively large impact on your dependent variable. You only end up with unbiased and consistent estimates if the correlation between the excluded variable and each of the independent variables equals 0. And that's generally not a very likely scenario. The issue of specification error is often very closely related to the choice of functional form. In particular, if we're choosing among alternative polynomial models, the choice between a quadratic and a cubic model is a question of whether that cubic term belongs in the equation or not. If it does and you leave it out, you've excluded a relevant variable. If it doesn't belong and you leave it in, then you've included an irrelevant variable. The same is true if we think about including various dummy variables or interaction terms. If the dummy variables or the interaction terms belong in the equation and you omit them, then you're going to have a problem of omitted variable bias. If they don't belong and you include them, then you've included some irrelevant variables. Similarly, the choice between linear models or piecewise linear models is also the same type of a choice of whether or not to include those particular variables in your model. Here's an example of how the choice of an incorrect functional form can result in some problems. If the true relationship is a quadratic relationship and we estimate a linear model, it's going to suggest that we have a problem that may actually look like autocorrelation in the model, when it's really just that we didn't include a quadratic term that really belonged in the equation. In practice, you don't know what the true model is. And as you work on your first econometric project, you don't know whether to include variables or not. When weighing the cost of including variables that are irrelevant or excluding potentially relevant variables, we should remember that leaving out important variables results in biased and inconsistent estimates and invalid t-statistics and all of the test statistics. So the cost of leaving out variables that may belong is really, really high, and it may mean that your model is completely invalid. Alternatively, if you include variables that are irrelevant, You may have somewhat less precise estimators, there's an efficiency loss, but you still can perform all appropriate hypothesis tests. So when making this choice, it's probably much better to err on the side of including variables that may be irrelevant rather than leaving out variables that may be relevant. One practice that's becoming increasingly common is a practice of data mining. It generally involves estimating a large number of alternative models to somehow find the best equation. A couple of things to keep in mind with this approach. It's used a lot when people are referring to big data analysis. One issue is that the usual test statistics are valid only if each sample is used for a single test. And by the nature of data mining, you're using the same sample for multiple tests. If you use the results of one test to help determine future specifications, the distribution of the test statistics will not generally follow the usual distribution. For example, if you use a t-statistic at one stage to determine what variables to include in a second regression, then the distribution for the test statistics will no longer follow a simple t distribution in that second stage. In general, though, the basic problem with data mining is that if you're using a 5% significance level and you start with, let's say, 100 variables that may be of interest, that may be related to your dependent variable, by the definition of the significance level of 5%, it means that 5% of the time you'll find results that are significant that really are not causally related. So what happens, and this is a tendency that everyone has when they first start working with statistics, is to try to throw many things into the regression, find what seems to be significant, drop the rest, and then report only results that are significant. The problem with that approach is while it may turn out to be significant because of type 1 errors in your initial regressions, those results are not likely to be very robust. If you tried working with a different sample, you probably would not get the same type of results. This type of process is also sometimes known as p-hacking. However, in practice, economists generally estimate more than one version of the model, and because of that, we should be careful interpreting the results from any single study unless we see replication in other studies. There are two practices that are generally considered extremely bad by econometricians, and many statistical packages offer these as an option. One is stepwise regression with forward selection. It's a form of automated data mining. The basic procedure for forward selection is you have a dependent variable, a set of potential independent variables, and the software will find which variable is most highly correlated with the dependent variable. It will include that in a regression, and then it will find which variable is next most correlated with the unexplained component of the dependent variable. And it will keep adding additional variables step by step until eventually the additional variables stop being statistically significant. The problem is that when you add the additional variables, if they turn out to be important, your prior stage that you used to generate the next stage estimates were based on computations that relied on biased and inconsistent parameter estimates and t-tests. And in general, virtually all econometricians argue against the use of forward selection processes such as this. Another practice, which is not quite as bad, is a backwards selection procedure, where you start with a model that includes everything, and then you progressively drop variables that are not significant and re-estimates the model. It's not quite as bad because at least you start with estimates that are unbiased and consistent, and you move on from there. However, most econometricians argue against this because, again, the t-statistics you get beyond the first stage are not generally valid for hypothesis testing unless you correct for the fact that your next stage estimates were conditioned on prior estimates. There are times, though, when you're trying to estimate a model where economic theory or knowledge of institutional characteristics provide little guidance on which variables to include. One case of that is when people are estimating what are called distributed lag models, where current levels of some variable are a function of past values of some other variable or past values of the variable itself. And if we believe that there's a relationship between the current and the past levels of some variable, we don't know how many lags you should include. And in those cases, econometricians and other statisticians will sometimes rely on things such as adjusted R-squared or other criteria that we'll discuss a little bit later in the course to guide the selection of how many of these lag terms you should include. But the problems are essentially equivalent to forward and backward selection algorithms that we just mentioned. In general, though, we can never use R-squared or adjusted R-squared to compare alternative models when the dependent variables are different. For example, if we're comparing a linear and a log linear model, because in that case, we're comparing the variation in different variables. And an adjusted R-squared criteria would only make some sense if we're measuring the same thing, if we're comparing apples to apples.